Hi, we appreciate you joining us again. Now, some technical insights into how this solution provides authentication, confidentiality, and integrity for the requester. Authentication means that the requester can verify that his computations are protected and the right code is executed. Data confidentiality means that the provider is not able to read input or output data. Data integrity means the provider is not able to modify input or output data without detection. Starting with an SGX enclave, the computation environment protected by SGX is called an SGX enclave. It is Graphene-ng based and encapsulates Blender. That is our target software. After receiving the task, the provider runs an enclave. The Graphene-ng enclave generates an RSA key. The private key is not revealed to anyone, while the enclave saves the public key in a file. The provider shares the public key with the requester. After downloading the data from the requester, the Graphene-ng enclave starts the computations using Blender. Blender finishes the rendering, and at the end, the enclave is destroyed. Intel's signature and attestation. The enclave generates a quote, a dataset describing the enclave. The quote is signed with keys sealed in the CPU and known only to Intel. The provider verifies the quote in the Intel Attestation service, which signs it. The provider passes the quote and IAS's signature to the requester. The requester verifies that the quote was signed by IAS. This way, the requester validates that the quote was generated by the enclave and all the data in the quote comes from the enclave, ensuring that the computations were performed by the enclave, not emulated. Intel's signature is the proof that the quote was generated by real SGX. Intel only signs the quotes that were signed with keys sealed in the CPUs, validating that the provider runs the right code. The quote contains the enclave's hash. This way, the requester knows that the provider runs the enclave that was ordered by the requester. The requester needs to know the enclave's hash a priori. Protection of the data transmission. In order to exchange data with the Graphene-ng enclave securely and efficiently, the requester generates a symmetric key. At this point, it is known only to the requester. The symmetric key is encrypted with the Graphene-ng enclave's public key and sent to the provider. The hash of the enclave's communication public key is written in the quote, so the requester knows that only the enclave can decrypt it. The provider handles the encrypted symmetric key to Graphene-ng enclave. The enclave decrypts it. At this stage, the requester and the enclave know the symmetric key. The requester has unencrypted input data, the scene. He encrypts the scene with the symmetric key. The provider receives encrypted data and passes it to the Graphene-ng enclave. The enclave decrypts it with the symmetric key and performs computations. At the end of the computations, the enclave encrypts the results with the symmetric key and gives the encrypted results to the provider. The provider returns the results to the requester. The requester decrypts the data. Only the requester and the enclave know the decrypted data. Thank you for watching Golem's demo.